part B.1, in this part, I want to explain project 2, our optional project, a little bit. Especially, I want to talk about the main method, because when we extend the repeated squaring method from the power of 2 case to the general case for the logarithmic Fibonacci number calculation algorithm, that main algorithm, main method, main step, mainly I want to talk about that. All right. First, so this is the Horner's rule based method. So in our lecture, so we studied this one. So if you can, first, this looks a little complicated, right? But actually, if you understand it, not that complicated. So if you can understand the whole thing and you can also implement it, that's good. Okay, that's good, no problem. Yeah. But some students may not be able to understand. Yeah, I noticed that. Yeah. So in that situation, here I recommend another simpler method. Yeah. So this one, when I graded project 1, many students already did this part. Yeah. So I think they found from the web, the logarithmic, the general, the idea basically the same. Yeah. Basically, different ways to, the idea almost the same. So here I recommend this simpler way. So for those students who have not tried it, probably if you feel simpler, you can try this way. Yeah. Here I just explained the main method, matrix power method. All right. Here, one version, they do not just use formal matrix. They just use 2D array for matrix. So in other way, they do not define a matrix class. Yeah, try to simplify it. Okay, those students, they try to simplify. They just use big integer 2D array, 2 by 2 2D array to represent matrix. Now, that's okay, but they just define other special matrix multiplication method. Yeah, that's okay, no problem. Yeah, many students choose that way, so it's okay. Yeah, some students use the matrix, class way, also okay. Yeah, here, suppose this matrix matrix class way. Later, I will talk about that. Switch to matrix class. But in this example, 2D array, 2 by 2. Okay. Also return 2 by 2 matrix result multiplication. But this one calculate the power. Yeah. So you provide AR1. This is an initial matrix. Okay. Initial matrix. So that is our 0, 1, 1, 1, right? So our initial matrix in this special format. Then integer power, exponent number, any positive integer. Could be even, could be odd. Okay, all right. Then this method is called recursively to implement power of a matrix. Recursively to implement power of a matrix. Yeah, so here you can see when we use it recursively, we take care of the, even odd case. Even that's easy. We can split evenly, right? But the odd, remember odd, we cannot split evenly, but there is a extra step we can do to, make it up. Yeah. All right. So let's look at the logic. First, this is the base case, right? Base case. Yeah. So when power equals 1, just return ARR1. Yeah. Okay. Yeah, that's simple. All right. Otherwise, power number greater than 1. Then, now we consider the special case. All right? Yeah. First, create a temporary array. This temporary is the square of initial array, 2D array, or matrix. Initial 2D array or matrix. First, you calculate that. Pretty easy. All right. So then, mod 2, power number mod 2. Check the remainder equals 0 or not. If equals 0, that's the even case. So this is even case. If it's not equal to 0, that's the odd case. Okay, odd case. All right. If it's the even case, then we can split evenly, right? Power evenly. Okay, yeah. All right, so that is 2 to the a to the n equals a squared n over 2. That idea. Okay, yeah. So this time, power initial matrix becomes temp, but exponent number is reduced by 1/2, power over 2. So you call it recursively. So this is the recursion step. Okay, recursion step. So you can see the same as the original power, but you reduce the power number. So if you keep doing that, eventually you will get the final answer easily. Okay, all right. But for the other case, yes, other case, you do integer division, this x integer division. That means the remainder 1 is taken out, right? Remainder 1. So you do not look at the remainder, that 1. So you take 1/2, but drop the fractional part. All right, so that's x. Yeah. Then you do multiplication, okay? When you do multiplication, AR1, yes, okay? AR1, so that matrix, because the reason you multiply this one, this corresponds to the remainder part. Remember, when you drop the remainder part, but in the final calculation, you need to add it back, the remainder part, okay? After you take away the remainder part, that one remainder, then you have the even number, right? So then you split. So this way, because you have even number, so that number divided by 2, okay? So then the temp, yeah. So you recover to the original power. So in this way, when you call recursively, right? Eventually, you will get the answer. Okay, the answer is correct. Yeah, the implementation is simpler to our Horner's rule-based version. Okay, yeah. So here, yeah, this is simpler than our Horner's rule version. Okay. All right. Yeah. So if you can understand this version, you can implement it. Yeah. But yeah, when you implement, if you do not use 2x2 array, if you use matrix, you need to replace the 2x2 matrix by your matrix data structure. Okay. Yeah. So that's the adaptive part you need to do. Okay. You need to do some adaptation. Okay. Yeah. But that part is very easy, straightforward. All right, yeah, I think you can do it. Try your best. Yeah. You have some time today, tonight, but you have the whole day tomorrow. So if you can try, you can earn up to 3% extra credit. That's a lot. Okay, try your best to earn it. Yeah. All right, so let me stop explanation here.